we're going to take what we've learned over the last few days now, this whole two-dimensional vector analysis, and we're going to apply that to some more concrete problems, some more practical problems beyond add these vectors together. Okay, I first want to define a couple of terms. The first term is what we call relative motion. What do we mean by relative motion? What do we mean by relative, first of all? Not the kind of relative that you don't want to come over to your house because they smell a little bit and they kind of annoy you. Okay, not that kind of relative. Okay? Relative in terms of physics. Relative to something else, right? As compared to something else. Measured from something else. That's what relative motion is. I had a question for you here now. If we have an airplane, Blue Jays just clinched the AL East division last night or yesterday afternoon. Okay, so they're going to the playoffs this year. They're in Baltimore, I think it is right now. They're going to fly back from Baltimore in a few days, back to Toronto. And maybe they're going to, I don't know, maybe they charter a plane and maybe the plane's a little bit late. Maybe one of the pitchers has to practice while on the airplane. I wouldn't recommend that, by the way, throwing a baseball while you're on an airplane, especially if it's a commercial airplane. Something bad might happen to you if you start throwing baseballs on commercial airplanes. But let's pretend for a second that this airplane is traveling at 800 kilometers per hour. One of the Blue Jays pitchers throws a baseball inside of it at 100 kilometers per hour. What's the velocity of the baseball? What's the velocity of the baseball relative to, I won't even say relative to what. What's the velocity of the baseball? Yep. Could be 900 kilometers per hour. Good question. What direction did he throw the baseball? Right? The airplane is moving to the east. He threw the baseball at 100 kilometers per hour. It could be 700 kilometers per hour, right? Could be 900, could be 700, depending upon the direction he threw the ball, if we're measuring the velocity of the baseball relative to the ground. If we measure relative to the airplane, it's 100, right? Any way you look at it. So it could be 100, it could be negative 100, it could be 900, it could be 700, relative to one thing or another, and depending upon the direction that the baseball was thrown. Okay, relative motion is that motion as compared to something else, as compared to the airplane, as compared to the ground. How did we get the relative velocity? Regardless of whether it was supposed to be relative to the ground or relative to the airplane, regardless of the direction, we added the vectors together, right? 800 plus 100 is 900. 800 plus negative 100 is 700. We added vectors together. What if we have a relative motion problem in two dimensions? What if he threw the baseball to the north? So the baseball is moving to the north, the airplane is traveling to the east. How do we solve that problem? Well, we know how to add vectors together in one dimension. We also know how to add vectors together in two dimensions. That's what we've been doing over the last few days. So when we're adding vectors together, when we're finding relative motion in one dimension, we add vectors. When we're doing it in two dimensions, we also add vectors. But to add vectors, we have to draw a vector diagram. What's the goal? Let's get a right-angled triangle. Now, when we're solving these problems, we're always going to have just two vectors. Okay? Good news is we're not going to have to deal with a problem where we have 4 or 5 or 6 different vectors. Two vectors, which means we're going to have 3 lines. 2 vectors and then a resultant vector. The 2 lines we draw them as solid lines. The resultant vector we draw as a dotted line. The reason we're going to do that is because it makes things more clear for us as we're solving these more practical problems. Solid line vectors, dotted line vector. 3 vectors might look like this. Sometimes we drew, when we were working on the problems over the last few days, the resultant vector dotted. Sometimes we do it in another color. Now we're always going to draw it dotted. It's not a huge deal. But I'm going to refer lots to the solid line vectors and the dotted line vectors, and I want you to know what I'm talking about. Why did we distinguish between solid and dotted line vectors, the component vectors and the resultant vectors? Well, because when we're solving these relative motion problems, there's a lot of different vectors that can exist. There are the solid lines and the dotted lines. We're going to give some examples of what we see as solid line vectors. Okay, when we're solving a problem where the question says the pilot of the airplane aims her plane to the north, we make that a solid line. If the captain of a ship heads to the west, we'd make that a solid line vector. If there's a wind of 30 kilometers per hour to the east that carries the airplane off course, we'd make that a solid line vector. If there's a river current that makes the swimmer go off course as he's trying to swim across the river, we'd make that a solid line vector. The airspeed of an airplane, how fast an airplane can travel in the absence of wind, we'd make that a solid line vector. Hey, when I get on an airplane, I always, I don't know if WestJet does this, but I know Air Canada does this. You read that magazine, the back of the magazine, it has these pictures of all these different airplanes that they fly, along with some specifications of those airplanes, including the size of them and the number of passengers and the airspeed of these airplanes. Okay, that's how fast it can travel when there's no wind. How fast it can travel in still air. Okay, if we're given the airspeed of an airplane, that's a solid line vector. Okay, that's one of the component vectors, the solid lines. All of these things, if we're given, are going to be solid lines. Basically, if it's something, if it's a vector that contributes to the motion of something, it's a solid line vector. Okay? The wind contributes to the motion of something, right? You're in an airplane, okay, going this way, the wind's going this way, you end up going down here somewhere, right? The wind contributed to where you went. Where you were aiming contributed to where you went. We're going to make those solid line vectors because they're contributing vectors. They contribute to where we want to go. Our dotted line vectors, they don't contribute to where we go, they're where we go. The airplane actually goes directly north or wants to go directly north. What's the velocity of the airplane relative to the ground, or the velocity of the ship relative to the shore? These are not what contribute to where I go. These are where I go. We're going to make those dotted lines. So if you think you might have trouble remembering these 6 things, I want you to remember these 2 things. Does it contribute to where I want to go? Or is it where I want to go? If it contributes, it's solid. If it is where I go, it's dotted. Hey, best way to deal with this is to do a question. You're going to have to copy this one down, unfortunately. It says the pilot of a plane heads directly north to Edmonton at a velocity of 200 kilometers per hour. However, there's a wind, and that wind is blowing to the east at 50 kilometers per hour. We want to know where the plane actually ends up. You can imagine if you're aiming to the north, but there's a wind, a strong wind at 50 kilometers per hour to the east, you're not going to end up going north, right? You're going to end up going somewhere else. It's like, how many people have their driver's license here? Anybody? Okay, a few of you do. You're driving your car north towards Calgary, and there's a strong wind. What do you find yourself doing if there's a strong wind to the east coming off the mountains? What do you find yourself doing sometimes with your steering wheel? Kind of push against the wind, right? You look at your hands on the steering wheel and the level of the steering wheel, it's going left. Not straight left, right? But you're aiming in one direction to compensate for the wind that's taking you off course. So the wind takes you away from where you're aiming. We want to know where the plane actually ends up going here. Now remember those solid line vectors and dotted line vectors. There's always going to be 2 solid, always going to be 1 dotted. The plane heads north at 200. Does that contribute to where I go, or is that where I go? If I'm heading north, but there's a wind, do I end up going north? No, city? No? So that's contributing to where I'm going, right? It's not where I'm actually going, it's contributing to where I'm going. So we're going to make that a solid line vector. Let's say 200 kilometers per hour. Wait a second, that's the first time we've had a vector that wasn't meters, right? Is velocity a vector? Sure, we can do vector diagrams with velocity as well then, okay? Okay, aiming 200 kilometers per hour north. There's a wind of 50 to the east. Does the wind contribute to where I go, or do I actually go to the east? It contributes. So I'm going to draw that 50 kilometers per hour as a solid line, right? Maybe right here. Does that work? Good. Excellent. Okay, what's wrong with this? It should be front to back, back to front. Okay, I can't draw it there. That's front to front. Okay, what I can do is draw it right here. Okay, now it's drawn front to back. Now my resultant vector, which is where I actually end up going, which is what I'm trying to find here, right? Basically the velocity relative to the ground, is a dotted line. And the dotted line goes from start to finish, the resultant vector. Where do I end up going? Well, let's find this angle and let's find the hypotenuse here. Let's say C is going to be the square root of 200 squared plus 50 squared. And let's say theta is going to be the inverse tan function of opposite over adjacent, 50 over 200. Where'd you get there, theta totus? 14 degrees? For theta. 14 degrees. Anybody agree with that? Yep. You got 14 degrees here. Good. That would be 14 degrees what of what? East of north, right? It's measured from the north axis, but it's kind of going to the east from the north. 14 degrees east of north. What about this side of the room? Stephen's side of the room. Stephen, you got that one? 206, which would technically round to 2 digits, 2.1 times 10 to the 2 kilometers per hour at 14 degrees east of north. Hey, you can imagine, if you're a pilot, maybe it would be useful to know something about vectors. In an ideal world, there's no wind, there's no problems like that at all. But the world isn't always ideal. You're flying and there's a wind of 50 kilometers per hour to the east. You know what? It might be useful to know where you're going. It might be useful to be able to do a vector analysis here. Let's try another one. This one says, the captain of a ship aims her ship east at 20 kilometers per hour, but there's a current of 10 kilometers per hour that puts the ship off course. Where does the ship actually go? She aims her ship east at 20 kilometers per hour. Is that where she goes, or does that contribute to where she goes? Kenway, is that where she goes, or does that contribute to where she goes? Yeah, that contributes to where she goes. That helps her get to a certain place, but it's not where she ended up going. So that's going to be a solid line, right? She aims her ship east. Solid line vector to the east at 20 kilometers per hour. There's a current of 10 kilometers per hour. That was supposed to be to the south. Didn't say that, but it's supposed to be to the south. Is that current of 10 kilometers per hour to the south, does that contribute to where she goes, or is that where she goes? Yeah, good, it contributes to it. So we're going to draw that as a solid line vector right here, right? 10 kilometers per hour to the south, right? Is that right? What's wrong? Good, I've drawn it front to front, can't do that. Let's switch it around here, make it front to back. My dotted line vector, that's where I actually go, or where she goes. We're going to draw that as a dotted line there from start to finish. Label theta, label C. We're going to say C is 20 squared plus 10 squared. And theta is the inverse tan function of 10 over 20. This time, Stephen's side of the room is going to find theta, and Thoda's side of the room is going to find the hypotenuse C. Let's see, Steven's side of the room, what do we get for theta here? Anybody on this side? Go ahead. It's 27 degrees. What are we going to call that? 27 degrees of what? South of east. Good. Now, you could have drawn it like this, right? 10, 20, that would have been fine. But if you do that, you got to make sure you calculate that angle separately, differently. You're going to find that that one would be 63 degrees east of south, not 27 degrees south of east. Equally as correct, just different number. What do we get for this one? 20 squared, 10 squared, going to be something like, I don't know, 23, 24, 22? 22 kilometers per hour at 27 degrees south of east.